Strategy for solving related rate problems. First, you want to read the problem carefully, generally at least twice. Second, you want to draw a diagram or a picture. It helps you see what's going on. Third, you want to assign variables to all quantities that are changing and label all constants in the picture. Very important, we're going to talk about this, but once you have the picture, it helps to kind of figure out what's going on. Next, you want to write down the givens and the wants in mathematical notation. These will likely include rates of the form of this. If you notice, these are all derivatives, right? That's what a rate is. It's a derivative. So dHdt, drdt, if you notice, are also all over dt. That's because in related rates, what we do with respect to time. We're talking about a rate here, so it's over time, some form of time. So it's always going to be one of those. When you talk about a rate, how fast, how much is it increasing, it should be a rate. We can also add, don't forget to add the constants like x, r, and h. Sometimes they're constants, sometimes they're variables, so you gotta watch out. Right, general primary equation that relates to variables. It is called related rates, so we want to relate the variables. This is where your formulas come in, your area formulas, your trig formulas, all that good stuff. If any quantities in the equation are constant, you may replace the variable with the actual number. Again, that's only if they're constant. That doesn't happen very often. When they're constant, it makes life so much easier. It makes it a much easier problem. But most of the time, like we said, you can leave them as variables. You would need to use geometry. Sometimes you can need to use geometry manipulate the formulas. Like you can have more variables than you need, and we like move around stuff. We'll see that more in the next video. Once you do all that, you can use the chain rule and implicit differentiation to take the derivative of both sides of the equation with respect to time. Always with respect to time. And then once you have that, you just substitute the given data and solve for what you need. After that, just round your answer and make sure it makes sense. So let's do an example. Example 1. The size of a square increased at a rate of 2 inches per minute. And our first question here is how fast is the area of the square increasing when the sides are 3 inches. So let's kind of go over that again. The size of a square increased at a rate of 2 inches per minute. So we're talking about a square. So let me draw it. We have a square. We know squares have 4 right sides and 4 congruent angles, but we just go to the sides for now. We know sides are increasing at a rate of 2 inches per minute. So this is label a side. You can make it anything you want. We'll say S. And it's the sides are increasing at a rate of this. So my side's increasing at a rate. So remember, it's a rate, so that's ds dt, because my side's increasing at a rate of 2 inches per minute. So that's my first given. Right, my given is sides increasing at a rate of 2 inches per minute. It's a side, it's increasing at a rate, so ds dt. And the question says, how fast is the area of a square increasing when the sides are 3 inches? So what we're looking for is right here. How fast is the area increasing? Notice it said increasing, so another rate. We're talking about the rate of the area. So that's going to be dA dt. That's what we want. I want to know what dA dt is. How fast is the area increasing? When the sides are 3 inches. Now here's the thing. When s equals 3. That's not a constant. Our sides are increasing, so they're not constant. This just says when the sides happen to be 3 inches, how fast is it increasing? So it's something we're going to plug in after we do our work, not before. This is not a constant, so we'll plug this in after. So the next thing we got to do, right, we have a graph, we have stuff labeled what we want. Let's try to relate these two things. I got to relate a side of a square with the area of the square. Well, there's the formula that should kind of go with that, right? How do you find the area of a square? Area equals side squared. Because it's an area, right? You just multiply the side times the side, so you get the area. That's our equation. Alright, once we have our equation, we can plug in any constants. I don't actually have any constants. Area is not a constant. Sides are constantly increasing, that's not a constant. So all we do now is take a derivative. We take d of dt to both sides. That's implicit differentiation. Derivative a is just 1, but the wrong variable. dA dt equals derivative s squared is 2s, but the wrong variable. ds dt. Right, some implicit differentiation. And now we just plug in what we have. Right? I have ds dt is 2 inches. Almost plugged in for the wrong thing. It goes here. I have s is 3 inches, so that goes in for s. And I'm looking for dA dt. So I have this. dA dt equals 2 times 3 times 2, also known as 6 times 12. Now I gotta have my units. So it's actually fairly easy, but let's talk about this in general. What did I find? I found the area. Right? So actually I found the rate of area. So area by itself is inches squared from my inches, but it is a rate, so you're not gonna divide it. It has to be a fraction, so you can divide it by minutes. So that's the rate just looking at the problem, what we're doing. If you want to do it really the way you're supposed to do it, well, side here was inches, and my rate here was inches over minutes. Right? So I had 2 times inches over minutes got me 12 inches squared over minutes. That's the answer. Let's look at the next one. Same idea. How fast is the area of the square increasing when the square has an area of 25? Right, so same given. ds dt equals 2 inches per minute. My want is different. I want how fast is the area of the square increasing. Well, actually, it's the same. I want dA dt. Exact same want, actually. But the other given is different. I want when the square has the area of 25. So I want this one area equals 25. Right, so let's flip it again. Not a constant, right? Area is constantly changing, size not constantly changing. We're going to use that at the end to plug stuff in. But other than that, it's the exact same problem, right? So what's our equation? Well, area equals side squared. Let's take a derivative with respect to t to both sides. d of dt. So I'm going to get 1 dA dt equals 2s ds dt. Do you notice an issue though? Oops. I want to look for dA dt, that's good. I have ds dt, that's 2. I don't have s. But I do have the area equals 25. I could use this to find my side. Right, we have this formula right here. Area equals s squared, so if I know the area is 25, it must equal s squared. Square root it. S equals plus and minus 5. We're doing the side of a rectangle, so only plus 5 makes sense. So now we can plug our stuff in. We have s, which is 5, I just found out. We have, well, 5 inches to be correct. We have ds dt, which they gave us up here, 2 inches per second per minute. So I plug that all in. I get dA dt equals 2 times 5 inches times 2 inches per minute, which gets us 10 times 2 is 20 inches per minute squared. Inches squared per minute, sorry. And that's the rate at which our area is changing. So every minute it's increasing by 20 inches squared. So let's move on to the next one. Now that our feet wet. Example 2. The radius of a circular oil spill expands at a rate of 3 meters per minute. So question A says, how fast is the area of the oil spill increasing when the radius is 45? So let's look at what we're talking about here, right? The radius of a circular oil spill. So we're talking about a circle, the radius. So here's my circle. I have a radius. And look what it tells me. The radius of the oil spill expands at a rate of 3 meters per minute. So again, notice the rate. We're talking about the radius, so dr dt. It's a terrible R. dr dt equals 3 meters per minute. And what do I want? How fast is the area increasing? So again, dA dt is increasing how much? When the radius is 45. Right, so my given is dr dt equals 3, like how much my radius is increasing. So it's increasing at a rate of 3 meters per minute. It's pretty big. I want to know how big is the area, how fast, my mistake, how fast is the area increasing. That's why it's dA dt when the radius is 45. So again, 45 is not a constant. It says, hey, when it happens to be 45, because my radius is expanding, what's the area? Or how fast is the area increasing? So we got to relate these two things. I got to relate radius with area. Well, area of a circle relates to those two. Area equals pi r squared. Right, so that's my formula. And then we always do the same thing. We take the derivative with respect to time on both sides. On the left side here, the derivative a is 1 dA dt is the wrong variable. On this side, pi is just a constant, it's just a number, so you just leave it there. So it's pi, derivative r squared is 2 r, but wrong variable, dr dt. So that's my derivative. And now we just plug in everything we have. I have the RDT right there. Plug it in. I have my radius I want. I want it at 45 right there. That's all I need. So let's plug everything in. So it's going to be 45 meters. The RDT is going to be 3 meters per minute. If you multiply it all together, I get 45 times 2 is 90. 90 times 3 is 270. Pi. And then we have, look at our units. Minutes and minutes per minute. Meters and meters per minute. So meters squared over minutes. That's how fast my area is increasing. So every minute, it's increasing by 270 pi meters squared, which is pretty fast. Pretty big. So that's the first problem. Second problem. The radius of the spill, if the radius of the spill is 0 at time 0, how fast is the area increasing after 5 minutes have passed? So that's a little funkier. So the radius of the spill is 0 at time 0. So when time equals 0, the radius equals 0. How fast is the area increasing? So the ADT, that's what I'm looking for, after 5 minutes. So when time is 5 minutes. Now we still have the exact same given. We still have the fact that the radius expands at a rate of 3 meters per minute. So the RDTs are given. And just like before, we got to relate these two things. Got to relate area with radius. Well, exact same formula works. Area equals of a circle is pi r squared. When I take a derivative just like last time, we get the exact same thing we got last time. So the ADT equals 2 pi r dRdt. Right, and we want to plug everything in. Just kind of like last time, there's going to be one issue. Right, we're looking for this. We have this guy. Do not have the radius though. So let's think about how we find the radius. I know the radius is 0 when time 0. And I want to know what the radius is after 5 minutes has passed. Do we know how big the radius is getting though? Like how much is it increasing? Up here. Every minute it's going up 3 meters. So at time 0, my radius was 0. After a minute, it's increasing by 3 meters. So it's going to be 3 meters. After 2 minutes, you increase another 3 meters. So it's going to be 6 meters. Right? 3, 9, 4, 12, 5 is 15 meters. So when time equals 5, the radius is 15 meters big. Sorry about that. So I'm really bad at that. Right? So when time equals 5, the radius is 15 meters big. That's how you do that. Now it's a little weird, but that's the way it works. It's like, hey, it's increasing. I know my radius is increasing at 3 meters every minute. It's been 5 minutes, so 3 times 5 is 15. So that's my radius. Gotta use some logic here. So then, just multiply all together. 50 times 2 is 6, 30. 30 times 3 is 90, 95. And then again, units, I got meters per minute, so I get meters squared per minute. That's your next related radius problem. Let's do a couple more. Actually, let's do one more. So let's look at this one. The height of a rectangular prism with a square base of side length 5 inches is growing. How fast is the height increasing when the volume of the prism is increasing at a rate of 200 inches cubed per minute? So there's a lot to unpack here. Let's look at it again. The height of a rectangular prism. Okay, let's draw that prism. Don't get scared. It's just drawing a prism. It's not actually coming out. I choose this 3D effects. There's my rectangular prism. I know it has a square base of side length 5. Now most of the time I would write like a variable here, but I know the bases are 5 inches. So these are constants. So these are going to be 5 and 5 to square. The height of a rectangular prism is what I'm looking for. The height of a rectangular prism, the square base is growing. So I don't know the height, but I know it's growing. So I'm going to put the height as h. Again, I know the square base is 5, but the height I have no idea. Look at the question. How fast is the height increasing? So my want is the rate at which this guy is increasing, the height. So that's going to be dH dt is what I'm looking for. Right? How fast is the height increasing? Right? Notice it's height increasing, so dH dt, not just h. When the volume of the prism is increasing at a rate of 200 inches cubed per minute. So we're talking about the volume of a prism, and it's increasing. So again, the rate of the volume. So that's going to be dV dt is what I have, the given. Right, so they gave me the volume of which the prism is increasing. It's the rate of the volume. So that's why it's dV dt. Just like how they want me to find the how fast the height increasing. So the rate of the height, dH dt. So that's what I have to play with. Right, now I got to find a formula that relates these two, hence related rates. Well, we're talking about volume of a prism. So the volume of a prism, as I said, taught you in geometry, volume of anything is just area of the base times height. Unless it's pointy, then it's 1/3, but in this case, it's normal. So the volume is area of the base times height. My height, h. So that's just going to be h. Area of the base, well, my base is these guys right here. Now, lucky for us, our base in this case is a constant. They say it's square base of side length 5 inches. That's not going to change. My base is just going to be 25. 5 times 5 for people bad at math. Right? So the area of that base right there is 5 times 5 is 25. My height is right there. My volume is this. That's my equation that relates to two functions. Volume equals area of the base times height. Area of base happens to be a constant in this case. Makes life easy. And my height is constantly changing. And what do we do next? We do what we always do. We take the derivative of both sides with respect to t. Right, derivative of v is just 1, but wrong variable, dv dt. Derivative of 25h is this going to be 25, but wrong variable, dh dt. So that's my equation. Right, and then we plug stuff in. So let's see, I'm looking for dh dt, so that's going to stay there. I have dv dt is 200 inches per cubed, inches cubed per minute, so 200 inches cubed per minute equals 25. By the way, the unit's 25. These are 5 inches and 5 inches. So it'll be inches squared times dh dt. All I gotta do now is divide it. So divide both sides by 25 inches squared. 200 by 25 is 8. So 8. I'm going to talk about the units in a second. Equal dh dt. So let's talk about units real quick. So one of the last things we're going to do. I'm very bad at that. I'm sorry. So let's talk about units real quick. So last thing we're doing today. Now you're supposed to do the units as you go and figure it out. That's all good and great. I can always figure it out just from the end. I'm doing dh dt, right? That's height. Height is inches here. That's time. Time is minutes. So this is me inches per minute. That's all it is. If it was area, I know area is inches squared. If it was volume, I know volume is inches cubed, because volume is always cubed, area is always squared. Then if it's over dt, that's your minutes, that's your time. So it's not as hard as it looks. It's like, oh, height, that's a single unit, inches. Time, that's in this case was minutes. And there you go. If you did look based on the mathematics, I had inches cubed over minutes divided by inches squared. Well, these canceled out, and I got inches over minutes. Just like I had here. And that's it for this part of related rates. More to come.